Okay, thanks, Andre. My name is Sam White. I'm a grad student in PPL, and today I'll be talking about adaptive MPI, giving an overview of its various features, and then concentrating on some more recent work on the runtime. So the motivation behind AMPI, similar to Charm++, is that as we head towards exascale, there are these trends towards increased variability, and that comes in two different forms. So variability in terms of the hardware, so different things, different latencies at different layers, failures, and increased node parallelism. In terms of software, applications themselves are becoming more complex and more dynamic. So you have adaptive mesh refinements, particle movements, and subscale simulations that all manifest in variability. And the natural question arises of how should applications respond to this? One answer is incrementally. So this is a common approach where you have an existing code. It's already been in production for several years or many years, written on MPI. So in order to get some sort of load balancing, you add node-level programming API that can take care of that for you. So that's OpenMP, Cocos, or it could be MPI Shared Memory or something else. The other alternative would be to rewrite your application, and this could be done incrementally with some interoperability features, or rewrite the entire application, which is infeasible for many projects and codes. But this could be in different runtimes or languages such as Legion, Charm++, or HBX. Another solution that we support is to take your existing MPI code and run it on a different MPI runtime that supports more of the dynamic capabilities of Charm++. So adaptive MPI is our implementation of the MPI standard on top of Charm. And it really offers all of the basic Charm++ capabilities to MPI programmers. So that is overdecomposition, overlap of communication and computation, dynamic load balancing, and various strategies for fault tolerance. So first I'm going to give kind of an overview of AMPI's features, and then I'll talk about the recent work. So AMPI ranks, the way the AMPI execution model works is we take the decomposition that the user has already done in their MPI code, and we basically overdo that. So we virtualize the number of ranks so that the user can specify that number at runtime. So that's just an additional argument to the program. What this means is that you can have multiple ranks running on the same core, which then you can schedule based on the work that they have to do. So while one rank is waiting on a message over the network, you can context switch to another rank that actually has work to do. And the way that this becomes profitable is that the context switching between these ranks is fast. And that's because we implement ranks as user-level threads, which you can context switch between in a matter of a few assembly instructions. Another feature of AMPI is that these ranks are migratable at runtime across the different cores and nodes of the system. And this enables us to do dynamic load balancing as well as checkpoint restart for fault tolerance. Or if you don't want to, if you have a new application, you don't have to write checkpointing code and code to restart from that, you can actually just use this to do that for longer runs. To illustrate this, we have a picture here where this is sort of the traditional MPI model. You have one rank per core, or it could be per node. With AMPI, we overdecompose or virtualize these ranks so that you have multiple per core, and this brings in the need for scheduling. And in Charm++ and AMPI, our answer for scheduling is really message-driven execution. So when one rank sends a message to another, that message will travel over the network or through the process to the other side. It will be inserted into a queue, and then sometime later, once a rank says it's ready to receive that, we'll take that message out of the queue. Another feature of AMPI is its dynamic load balancing capabilities. So after running for a while, you might observe that some ranks in your job have more work to do than others. In MPI, it's all on the application developer to decompose their work properly and in a balanced manner. And to actually be able to rebalance at runtime is a very difficult thing to do in the programming model. But with AMPI, we can migrate entire ranks across the network from overloaded to underloaded processors. Of course, there's one caveat to AMPI's virtualization of ranks as use-level threads. And this example illustrates that. So this is what a lot of MPI codes look like. You have some global variables where you set maybe the rank and the size and possibly all sorts of other simulation state. But once you virtualize those ranks, there's a problem here. And that's that the rank, which is a global variable in this example, will be set by the first rank that gets to it to its rank number. And then if that rank then blocks and we context switch to another rank, that rank will update the same number. So there's a race on the global variables. This is due to the fact that global variables are defined at the process level. And so we need some sort of mechanism to protect against this. And we have a number of solutions. So the first solution is to refactor an application to not use global variables. This can be a pretty big task for production codes that have been written over the period of many years. Although it can be a pervasive change, it's very simple work to do, and interns can usually handle this refactoring. The second solution we provide is on ELF systems to actually switch out the global offset table every time we context switch between ranks. This is only portable to ELF systems. It has a couple other limitations too. Our favorite approach currently is to have programmers tag all of the unsafe variables in their program. So this is all the mutable global and static variables with a thread local attribute. So in Fortran, you can use OpenMP thread private, and in C and C++, you have the thread local keyword. And then every time we context switch, we just update one pointer to the TLS data. And there's actually some work in progress to have the compiler do this for the programmer. So the programmer doesn't even have to tag anything anymore. The compiler can just generate all of the globals as thread local. There are a couple other caveats to converting an existing MPI code to AMPI. The first is privatization. The second is you can have calls to AMPI-specific extensions to the standard. These are all prefixed with AMPI underscore, and the most commonly used one is AMPI migrate, which takes a flag that says if you want to do load balancing or you want a checkpoint. The third caveat, which I call 2.5 here, is specific to Fortran. So if you're working on a Fortran code, AMPI implements those MPI bindings. There are a couple extra small things you have to do. So first, you have to rename the program to be a subroutine so that AMPI can do its initialization first and then call into your program. And the second is if you have command line arguments that you're parsing, AMPI has to be made aware of those. The third one is something we've run into in production codes where they make heavy use of automatic arrays, which are allocated on the stack. And since we are allocating the stack on these use-level threads, you may have to increase the thread stack size, but that's just a runtime parameter. Okay.
Yeah. The thread privatization stuff you talked about, it's probably important to restate, and I hope you speak in the mic, that it is not necessary to do that if you're writing a program from scratch.
Yeah, if you're writing a new program, you can write it from scratch without global variables. This is something most modern codes already do, is avoid the use of mutable global state. It's good software engineering practice. And so if you are starting a new code, you can do that from scratch, and you can maintain compatibility with MPI and AMPI. Okay, next I wanted to show a quick example of what overdecomposition in AMPI means. So both synchronous codes, as Sanjay mentioned yesterday in his intro talk, often have these compute-communicate cycles or phases to them. So the purple lines here are the all reduce. The red is a computation phase, and then the green and blue are point-to-point messaging. This is LULESH 2.0. And we see here that if you introduce a little bit of load imbalance to LULESH, the all reduce suddenly takes up most of your time step. And this is because it's a blocking all reduce call. If instead we overdecompose with AMPI, and here I'm just showing a single processor with multiple AMPI ranks on it. So these are the multiple ranks that are on this same core. Whereas before the all reduce took up most of the time step, now we can actually overlap this with other work. So here you can see what each rank is doing at a given point in time. So this rank gets to the all reduce first and blocks in there. Then another rank is scheduled that has work to do. It goes into the all reduce. And so you sort of pipeline the communication over time that way. And we can see this effect here, where on the top we have 1 rank per core, and on the bottom we have 8 times that. And the peak amount of bandwidth used on the machine is almost 4x less at the peak. So you don't actually need as much bandwidth from your network if you pipeline the communication over the whole time step. A little bit about how migration in AMPI works. In Charm++, you have to write these pup routines for all of your data types and chars. In AMPI, that's all automatic. So we have these user-level threads that have a stack and a heap. And we provide a special memory allocator called isomalloc that we allocate the stack and all heap data with, which basically allocates memory in reserved slots in the global virtual memory. So this requires 64-bit virtual memory and requires the OS to expose us things like mmap calls to map that memory where we want it to be. The nice thing about isomalloc is that when we migrate a rank, it's transparent to the user. Because the stack is also migrated, all the pointers into the heap memory are maintained. And so the user doesn't have to actually write any serialization code. To actually enable load balancing in an AMPI program, users just have to insert a call to AMPI migrate, link with the load balancer of their choice and isomalloc, and then at runtime they specify the number of ranks. That's the plus VP parameter and the balancing strategy. Okay. Next, I want to talk about more recent work on AMPI. So AMPI, just like Charm++, can optimize for communication locality. And by this, I mean you have a sort of hierarchical system where you have multiple things communicating that could be on the same core, could be on the same socket, could be on the same node, or maybe they're partners in the topology, neighbors in the topology. And so AMPI has potential at least to exploit this. And another interesting thing is that AMPI can actually do load balancing that takes into consideration the communication graph of the application. So this is a picture illustrating how AMPI works on modern shared memory node. So you'll notice that we have one operating system process that then launches several schedulers. This is basically SMP mode in Charm++. And we dedicate one thread to drive the communication on each process. And then as well as on each scheduler, you have multiple ranks. So you potentially have many, many ranks that are sharing the same address space with each other. When we looked at AMPI's existing performance in SMP mode of Charm, though, we saw some limitations. So AMPI was originally developed in 2001 and has sort of had up and down funding since then, and it's been used for various things like simulation, and mainly for applications with a lot of load imbalance. So when we looked at actually tuning AMPI for shared memory systems, we saw some sort of surprising things. So this is on Quartz at Livermore, which is a omnipath cluster with Ivy Bridge processors. And these are the three MPI implementations that are built there by default. So we have MVAPICH 2.2, Intel MPI 2018, and OpenMPI 2.0. And what we saw is that in the P1 case, so this is two ranks that are on the same core talking to each other, we were actually doing worse than what a normal MPI would do with two ranks communicating on two different cores between to each other. And then in the case that's more analogous to MPI, to a process-based MPI implementation, we were considerably worse in terms of latency. That was for small message sizes, and for large message sizes, it's basically even worse. We're over 3 times slower than the process-based MPIs. So we looked at actually why this is happening. Charm++ in SMP mode already optimizes for this for most applications. It can just transparently take advantage of that. But we weren't seeing that same benefit in AMPI. So when we looked at the latency numbers for AMPI, we looked at basically small messages and large messages and what the overheads there were. And we saw most of the time was spent in scheduling overheads for the small message case. And for the large message case, it's basically all spent in memory copies. When we looked at what we could actually do about these overheads, we saw that AMPI wasn't using Charm++ inline attributes on its entry methods. And so that every single message is going through the Charm scheduler. We looked at the overhead of the context switching between user-level threads, and we saw that AMPI wasn't doing as well as it could there. So Samyang Bak implemented a new user-level threads implementation in Charm++ on top of boost user-level threads. And this dramatically reduced the context switching time. We also minimized the number of context switches that AMPI does. So when you do an MPI wait all, AMPI would basically wake up the thread on every message it received. But if you just keep track of how many requests you have that you're blocking on, you can basically just wake up after you receive the last one that you're blocked on. Just doing these changes reduced the 0-byte message latency pretty much in half. But we still saw that even with inline tasks, AMPI performed poorly for large messages. So we reduced in half the time for small messages, but large messages didn't really change much. And the reason that was happening is because Charm++ messaging semantics don't really match MPI's messaging semantics. So in Charm++, messages are first-class objects. So if you're doing parameter marshalling, the arguments that you pass to the entry method are packed into a Charm message. But the application is free to actually reuse the Charm++ messages in its own buffers. And when you can do that, then whenever you have a message passed between two cores in the same process, Charm just passes the pointer to that message. And so it doesn't have to do any copies. And so in MPI, in contrast, messages are just buffers that the user owns that they just pass a pointer to, and then the size or data type. So there's basically 2 separate semantics to messaging there. To overcome this, we implemented a new zero-copy API in Charm++ that could expose the rendezvous protocol to AMPI. So Nitin Bhatt will talk about this later today, this API. But essentially, this allows us to send a short control message over, and then once we know the receive buffer, then we can copy directly from the send buffer to that receive buffer with no intermediate copy. And this optimization reduced the latency in half of the large messages too, because we basically reduced from 2 copies to a single copy. The other overheads that we saw in AMPI were due to the MPI message matching that we have to do. And we saw some ways to mitigate that, mainly by using memory pools inside of AMPI for commonly used objects. So this is for request objects and for the queue, message matching queue objects as well. And we optimize those for the common usage patterns of communicating with a small number of neighbors and then iterating over those objects as is done in like an MPI WADL. And this reduced the 0-byte message latency further. So now when you send a message in AMPI in the common case, you're not doing any dynamic memory allocation in the critical path. After all these optimizations, we looked at the performance again. And now we see more what we would expect. So if you're sending a message between two rings that happen to live on the same core, that's much faster, just over 500 nanoseconds. And if you're sending a message between two ranks that are in the same process, but on different cores, we're now competitive with process-based MPIs up until 2 kilobytes, and then above 2 kilobytes, we're actually outperforming them. So this is due to the fact that we don't have to call into the kernel or do an extra copy into shared memory. For large messages, we see similar benefits, where we're doing this user-space mem copy. And AMPI in the P2 case is now up to 2.3 times faster than all the process-based MPIs installed on that system on Quartz at Livermore. We also looked at bandwidth. And what we found was that on Quartz, none of the process-based MPIs could actually use all of the main memory bandwidth for point-to-point messaging. So we did this by looking at the stream copy benchmark, which is around 26,000 megabytes per second. And we saw all of the process-based MPIs top out at around 22,000. But AMPI, since all of the messaging takes place in user space, could utilize the full bandwidth here. We also looked at different systems. So on Cori at NERSC, on the Haswell partition, we're now down to 300 nanoseconds for messages in the same core and down to under a microsecond for small messages across two different cores in the same process. For large messages, it's again similar. Cray MPI does pretty well for large messages with XPMEM up until you get to extremely large messages of 32 megabytes or more. And again, for the bidirectional bandwidth, Cray MPI performed pretty well up until you got to the very large message sizes again. So to summarize this work, this is published at XMPI workshop at SC this past fall. Using user space memory for all of the messaging protocols in AMPI, we were able to get around 2x higher bandwidth and 2x improvements for latency of large messages. And so that concludes my talk. Tomorrow we can have an AMPI tutorial. We planned an AMPI tutorial. So if anyone is interested in that, come talk to me. We're not sure how many people are still interested in that, but yep, that's it for me.
Well, before we take questions, I thought I would give you one more piece of information. Just a few minutes before Sam started talking, we got word that the DOE has funded a significantly large grant for CharmWorks for development of AMPI. It'll go on for the next 2 years. So expect a lot more from AMPI. You have a right to expect and question us more. And after that. So congratulations to Sam and the people who worked on that. So a question. I have a question before that. A clarification. So we can consider this communication within a process between multiple what we think of as multiple ranks as an implementation of endpoints proposal. Isn't that so? Can you clarify?
So the only difference between the MPI endpoints proposal and AMPI is in AMPI we are creating all of the ranks before the program actually gets to its main. And in the MPI endpoints proposal for MPI 4, the user would have a call to make that would create the endpoints at any point in time. But we could implement the MPI endpoints API as well.
Okay. Questions? Yes.
I have a question on isomalloc. Do you guys just do that completely automatically for everything that's heap allocated, or the user should differentiate between whether I want to use isomalloc or not?
Yeah, so it's everything that the user heap allocates because we link in our own memory allocator. So everything that the user allocates will go through isomalloc.
So that's totally transparent.
Yeah.
That's just a command line argument, and that's it.
And we've thought about doing this for charm too to eliminate the need to write pup routines. Right now, there's a restriction in isomalloc's implementation that it only works for usable threads, but there's been some work on generalizing that for the user to be able to make specific calls to allocate using isomalloc.
Also, for everything in Charm++, so as you said, you would avoid having the client code write the pop routines.
Yeah.
There may not be necessary, or that may collide with what the user wants to do. Isn't that the case? Like, I don't want pop routines for everything I do, maybe.
Yeah, so that's
right?
one optimization that pup routines enable is that if you have state that you can reconstruct on the other side, you don't have to actually pup that, or if you have some read-only state somewhere. So AMPI actually does enable you to write pup routines, so that's an optimization, but isomalloc enables faster experimentation with it, so you don't have to write those all up front.
Thank you.
So, since we're talking about isomalloc, so this is just a comment for the charm people, right? Changa users see this message every time they run and say, oh, you're not using isomalloc, you might want to, and everybody gets confused.
Yeah, so the problem there is at charm initialization, we don't know whether you're going to use user-level threads or not. So that message is printed out. It says to use isomalloc sync on some plus isomalloc _ sync on some systems. But we could, there might be ways to better hide that from users. Yeah, that comes up a lot though.
What is the performance of isomalloc compared to really fast allocators like jemalloc? Because that's something like if you guys wanted to replace and force me to use isomalloc, that might be a deal breaker for me, actually.
Yeah, well, yeah, we're not forcing anyone to use it. It's just a way to avoid the need to write pup routines. But it's usually, it basically allocates a bunch of memory at first up front and then gives you slices of that. So it's within a couple percentile usually for any real application.
Yeah, but usually, so the default allocator in that GCC supplies is total garbage. So my question is specifically, how does isomalloc compare to really fast allocators like jemalloc or tcmalloc?
Yeah, we haven't done micro benchmarks of that specifically.
But I think it's fair to say that initial allocation in virtual memory is what we need for isomalloc, because basically isomalloc reserves that space essentially on all processes in the system in the virtual memory. It's not mapped. It's mapped when you migrate there, but it is reserved. Once that block of space, that address space is, and then on my process, I allocated a big chunk and for my object, and I'm giving you pieces of it one at a time using some allocator. That allocator can be any library you want as long as that library can be plugged there. So you can plug different malloc implementations onto it, isn't it? We might not have structured it that way, but I don't see any reason why not.
There's no reason why we can't do that. We don't support it right now, but
yeah.
Yeah.
So you use malloc right now?
tcmalloc? No.
Yeah, we noticed that using fast allocators is really useful.
Using fast allocator is really useful. Repeat his comments. So, okay, yep.
I have an even more. So isomalloc is for performance. If I don't use it, it's still going to be correct, the thread migration and all that, or not.
No, this is what enables the transparent thread migration.
So if that's not enabled, then that's not correct.
Unless you write pup routines.
I think we are mixing two different things. The stacks are always isomalloc allocated. Now, heap data structures can be, if you do them, allocate them yourself without using isomalloc heap, then you have to pup them.
Yeah, if you don't link in isomalloc, then you're only going to get isomalloc for the stacks, and then it's your responsibility to pup whatever heap memory.
Which I think is a good thing to do in a final optimizing phase of your application. May be good, especially if you have lots of dead variables that you want to kind of carefully weed out. Then you might want to write your own pup, but you can get the application up and running.
Still, if I don't write it and I don't use isomalloc, it's still going to be correct.
No.
No, it won't.
You can't migrate without pup routines and without isomalloc.
You allocate with a pointer to some data structure here, and you want to migrate to another process. How is that data structure going to go there? So,
It's basically a replacement for pup routines.
okay. Any other urgent questions? Otherwise, we'll take a break. 18 minutes break. We'll start at 11 o'clock. Okay. Thanks, Sam, again.